A few things you need to know about vertical stretch when writing equations. Vertical stretch factor determines the how stretched out this parabola is going to be. If you have, by the way, positive parabolas here, positive a values produce smiling parabolas, and negative a values produce frowning parabolas here. And I'm referring to particularly this value in each of the equations. And so I'm going to use this particular graph, and we'll practice here determining what is the vertical stretch or shrink factor, and then how do we write the equation. We've got a 0.23, and the next one is 3.4, and the one to the left here is 1.4. It's this one. Okay, so the first way we can determine what this is but just by referencing the graph. And if we kind of compare here, big A values, by the way, so positive looks like this, negative. Large A values have this effect, and then small A values, meaning decimals, have this effect. So small a, it actually scrunches it down, it squeezes it to get vertically shorter. And this, it's sort of like you're pulling it, stretching it tight, appearing as if it were skinnier. So a lot of students look at this as fat versus skinny maybe, but it's actually tall versus squat more officially. Now, to figure this out here, the first method is by interpreting the graph. And if you examine the vertex here and you take one full step to either side, left or right, we would have to go up one to reach that next point right there. And so that's a 1-to-1 proportion, and every normal parabola has that particular proportion. So when this occurs, if you measure from the vertex, the next major point should be over 1 and then up 1. That would be a normal A value. In this case, the default A is 1. And since this has no roots, we cannot write it in factored form. And we can't interpret B from just the graph of this. So really our only choice for writing the equation is from vertex form. And the H is this 2. So H is 2 and K is 3. And from interpreting the slope, so to speak, of that first point, we can fill out the A value and then just plug in the particulars to write this equation. Y equals X as the variable, 1 in front, but I won't even bother writing the 1, minus 2 is the H value squared on the outside to make it a parabola, and plus 3 is the K value. And that would be the vertex form. Now, if you instead wanted this, say, in standard form, you would have to expand this. And this is, by the way, satisfactory enough if your goal is just to write an equation. If your goal is to figure out the standard form, for whatever reason here, we have to do a little bit more effort to simplify some of these numbers here. So we actually have x minus 2 being squared, which requires the box method. X minus 2, x minus 2, x squared. And then we have this plus 3 at the end here. So this is actually x squared minus 4x plus 4, but plus that 3 on the end there. Really, so x squared minus 4x plus 7 would be the equivalent standard form. So that would be how you convert from vertex to standard form. And again, the A value is the same A value, it's still 1. So that's example 1. Okay, example 2 has the same vertex, 2, 3, but now it opens downwards, or is concave down, as they call it. That means the A value is negative, and if we measure here just from the vertex, and you go over 1, now in this case, it's a 1, we will go down 2 to reach that next point. And we have now negatively doubled the point values here from their original setup from the previous parabola. So same vertex, but now we have to stretch down twice as far to get to the next point. And that's a factor of -2. So when we go to write the equation of this in vertex form, x minus h squared plus k, the a value, if you go over 1 in either direction really, a is now -2. So negative makes it open down, and the next point is twice as far away here. X minus, that part's the same. The 2 is because of the x value here. This is the h and k, the vertex, plus 3. And so that's how you would interpret from the graph if there were nice even numbers there to read off of. All right, example 3 is yet another parabola that has a vertex at 2, 3. However, in this case, it is positive, and if we examine from the vertex and you go over 1, we would have to, instead of going up 1 as would be the default, we have to increase by 3. And so this has been vertically stretched by 3. And to accommodate that, here a is in this case 3. We can see that the larger this gets, a is 3, it does appear skinnier, although it's in fact growing taller. So writing the equation for this, we have y equals 3, x minus 2 squared plus 3. Okay, example 4 is same vertex, 2, 3. However, in this case, if we measure from the vertex, we go over 1, and then we have only increased by half. To increase from a y value of 3 to y value of 3.5, that would be up 0.5. And that means the a value, the vertical stretch, is in fact actually considered to be a vertical shrink. The equation, though, is very similar here. Y equals 0.5 x minus 2 squared plus 3. So really, if it's easy to see here, the next point is easy to interpret. You can just do a slope triangle and kind of figure out what that proportion is, and that is always the a value.